The universe undeniably expanded, stretching infinitely at first, before slowing down and continuing to grow at a much slower pace. Eventually, it evolved into the universe we recognize today. This concept is known as the inflationary model of the universe's origin, which is the most widely accepted and popular theory of how the universe began. However, some physicists argue that this theory doesn't fully explain the development of the universe. They suggest that the universe existed long before the event we consider the Big Bang, expanding endlessly into the past and future. While the universe continues to expand today, it was once contracting before the Big Bang. In this view, the Big Bang isn't a singular explosion but more of a transition, a leap from a previously contracted state to an expanding one. According to this hypothesis, the universe might continue its evolution, undergoing a cycle of expansion and contraction, with eventual collapses and new bursts of creation, possibly leading to another Big Bang in the distant future. Some physicists propose that the cycle could be endless, with the universe perpetually expanding, contracting, and re-expanding. This alternative view challenges the standard cosmological model, which posits that everything began with a Big Bang. Brian Cox, a prominent physicist, has questioned the notion that something cannot come from nothing, further complicating the theory of the Big Bang as the beginning of the universe. Recent discoveries by the James Webb Space Telescope have uncovered findings that contradict the idea of the Big Bang being the start of everything, prompting further questions about the true origin of the universe. If the Big Bang was not the beginning, then what was the universe's true origin? Could it have emerged from an event or entity yet to be fully understood? The idea of a universe without a clear starting point or end is not new and dates back to the work of Georges Lemaitre in 1927. While this theory challenges the traditional view, a minority of scientists still believe in the Big Bang as the origin of everything. Even with these questions, there is mounting evidence for the universe's inflationary period, an expansion that took place before the Big Bang itself. The Big Bang, in this view, represents the end result of what occurred during the universe's early evolution. The universe, at its infancy, was almost entirely empty, devoid of matter and photons. Space itself was filled with immense energy, which gradually evolved into the structure of the universe we observe today. Over time, this energy converted into matter and radiation, a transformation that occurred rapidly but not instantaneously. The temperature of the universe skyrocketed, rapidly cooling down from incredibly high temperatures to just a few degrees above absolute zero. This shift from radiation-dominated to matter-dominated periods marks the beginning of the universe as we know it. As inflation proceeded, the universe expanded rapidly. The speed at which the universe grew slowed down as it transitioned from a highly energetic state to one where matter began to dominate. This ongoing expansion would lead to regions of space where the energy began to stabilize into more homogeneous forms, with quantum fluctuations creating seeds of cosmic structure. These fluctuations, in turn, would give rise to galaxies, stars, and eventually planets. In the inflationary universe, the growth of spacetime is not uniform. The distance between any 2 points will continue to double over time, while the regions that are still expanding will move farther apart from each other. The energy present in the universe will continue to shape the evolution of these distant regions. Some areas will experience a slowdown in expansion due to the accumulation of antimatter and radiation, while others continue to expand freely. According to the inflationary model, regions of the universe where the expansion ceases will eventually become dominated by dark energy, which will further accelerate the expansion in the future. This ongoing process leads to a universe that continues to evolve and grow in size, even as the rate of expansion slows down. Some scientists speculate that the universe we observe may eventually become isolated from others, with no further interactions as it continues to expand. In this vision, the universe might have come into being through a cycle of repeated Big Bangs, each one giving rise to new regions of spacetime that evolve independently. The energy fluctuations of the universe create regions of overdensity and underdensity, which serve as the seeds for future cosmic structures, potentially leading to new universes. Immense cosmic designs remain hidden from our view, especially in the early universe, which underwent a massive, intense blast. Unfortunately, there are no perceptible inscriptions or records from this early stage that we can access. The earliest noticeable signals come from about 380,000 years after the Big Bang, once the universe had undergone further processes. While we can extrapolate to understand the initial density fluctuations, much remains a mystery in the story of cosmic evolution. Temperature fluctuations from the early universe are imprinted in the cosmic microwave background, CMB, providing evidence for the Big Bang's origin. However, several inconsistencies persist within the CMB and our current cosmological models, suggesting that there is something crucial missing in our understanding. These inconsistencies can be summarized in 4 key anomalies. First, on large scales, the universe does not behave as predicted. The light from the CMB is being lensed by gravitational effects, distorting and magnifying the microwave background. This lensing effect doesn't align perfectly with our advanced cosmological models, making it a significant challenge in modern cosmology. Secondly, the temperature variations across the CMB sky differ in a way that contradicts the assumption of uniformity in the early universe. This inconsistency raises questions about the universe's uniformity and its origin. Thirdly, the Hubble constant, which measures the rate of expansion of the universe, varies depending on whether it's measured from the CMB or from nearby stars, highlighting another unresolved issue. These anomalies indicate that our current understanding of the universe may be incomplete. One potential explanation for these inconsistencies comes from circle quantum cosmology, which is based on quantum gravity. In this framework, gravity is composed of particles known as gravitons. Circle quantum cosmology suggests that there is a minimum scale of space, around 1.0 times 10 to the power of -35 meters. This approach proposes that the universe could not have started from a singularity as suggested by traditional Big Bang models. Instead, the universe might have evolved from a previous universe that contracted and then expanded again, similar to a phoenix rising from the ashes. While the idea of a cyclic universe is not new, circle quantum cosmology provides a mathematical structure to support this theory, aligning it with concepts found in ancient cosmologies like Hinduism. If circle quantum cosmology is correct, the early universe could have had softer energy and density, leading to changes in the CMB that could offer substantial evidence of the universe's origins. This model could also help explain the observed anomalies in the CMB, such as the large-scale behavior of the universe and the lensing effects. These insights suggest that quantum gravity may have played a crucial role in the universe's early stages, challenging conventional ideas about its origin and behavior. The idea that the universe started with a bounce, rather than a singular point of origin, is intriguing but still requires more research. The role of quantum gravity in shaping the early universe suggests that our observations might be limited to specific regions of the cosmos, potentially obscuring a broader understanding of the universe's beginnings. This is an ongoing challenge, as highlighted by Dwayne Johnson, a professor at the University of Pennsylvania, who points out the difficulty in testing such theories due to the vast scales involved. Despite this, recent advances in circle quantum cosmology and its potential to address cosmic anomalies offer hope for solving long-standing cosmological puzzles. The debate over whether the universe had a singular beginning or whether it follows a cyclic model remains unresolved. Proponents of a singular beginning argue that the universe did have a starting point, but this raises questions about what triggered that event. Cyclic cosmology, on the other hand, proposes an eternal universe, with cycles of expansion and contraction, though this introduces the problem of entropy. Each cycle would result in an increase in disorder, conflicting with the idea of a timeless universe. New models attempt to address this issue by introducing large time gaps between cycles, allowing entropy to dissipate. Physicist William Kenny from the University of Buffalo argues that cyclic cosmology faces significant challenges, particularly concerning entropy. His research suggests that the universe likely had a specific beginning, as entropy would accumulate with each cycle, making a timeless universe difficult to reconcile. This ongoing debate fuels further exploration into the nature of the universe's origins and its ultimate fate. The future of the universe hinges on its composition, particularly dark energy and matter, which determine its fate. There are two primary scenarios: eternal expansion or eventual contraction. In the first scenario, the universe expands forever, with stars eventually exhausting their fuel and leaving behind remnants like white dwarfs and black holes. However, if dark energy is constant, this expansion would lead to a cold, dark end as stars fade and entropy increases. Alternatively, if dark matter is significant, the universe's expansion could slow and eventually reverse, leading to contraction and the possibility of another big bounce. In this case, the universe would go through cycles of expansion and contraction, never reaching infinite density or a final beginning, offering a more hopeful view than the cold, dark end. Regardless of the ultimate fate of the universe, our current moment in time is remarkable. It highlights our unique place in the cosmos and underscores the importance of understanding its vastness and inevitable reality. As we ponder the universe's future, we are reminded of the transient nature of our existence and the role that knowledge plays in uncovering its mysteries. Thank you for exploring these topics with me. Your support helps us continue to produce high-quality content, and we appreciate your feedback on modern subjects. Stay tuned for future episodes by subscribing and sharing. Until next time, keep delving into the mysteries of the universe.